Alrighty, so hello and welcome. Here is all the topics that we're going to be covering today. We're going to be doing writing equations, stoichiometry, molarity, electrolytes, including naming acids and bases. And then finally, we're going to do redox. All right, so the first topic is writing chemical equations. So we have a little practice problem for everyone to try. Write the balanced molecular formula for the reaction between chromium-3 nitrate and iron-2 sulfate. So everyone go ahead and try it out right now. And again, if you have any questions, please feel free to type them in the chat box. Okay, so hopefully you all had time to try out the equation. The first step that we need to take is to identify the chemical species. And you should have done something like this. Basically, since it's chromium-3 nitrate, we know that chromium will have a +3 charge. And nitrate, we should memorize this, will have a -1 charge. And then same goes for iron-2 sulfate. After that, you're going to want to balance the charges for each compound. So hopefully you should have gotten something like this. Chromium-3 nitrate with 3 nitrate ions. And then FeSO4 with only 1 of each atom for the compounds. And then it's always a good idea to double check the charges. For example, chromium will have a charge of +3, and since there are 3 nitrate ions, this side will have a charge of -3. So these will cancel out and will make a neutral atom, or neutral compound, which is what we want. And then finally, you're going to write the chemical equation. We are always going to start with our reactants and then draw the arrow to turn into products. So you should have written something like this. The reactants are here and our products are here, and we know to form this because opposites attract. So this negatively charged nitrate is going to pair up with the positively charged iron. And then this positively charged chromate or chromium is going to pair up with this negatively charged sulfate ion. So after we have that, the next step is to balance the charges of the new compounds formed. So you should have written something like this. So previously, when we made the new compounds, this isn't balanced because chromium has a charge of +3, whereas sulfate has a charge of -2. So when we balance the compounds, we have to make sure to add subscripts to check if this compound is balanced or not. And then the same goes for the iron-2 nitrate that we made. And then finally, we're going to balance the overall chemical equation. So we do this by adding coefficients in front of the compounds. So here, if we have 2 chromiums on this side, the product side, we need to balance the 2 chromiums on the reactant side. So which is why we put a 2 in front. And then the same goes for the sulfate. We have 3 on this side, we need 3 on that side. Same thing for the nitrate. If we have 2 on this side, if we have 6 on this side, we're going to need 6 on the other side. Okay? So next, we're going to write the total ionic equation for this reaction between chromium 3 nitrate and iron 2 sulfate. The important thing for this is that this reaction happens in water. So this is when you need those solubility rules. So please go ahead and take those out right now and try writing out the total ionic equation. And then again, if you have any questions, please feel free to ask them in the chat. We can read your comments or questions, and then we will address it if we do get any. Okay, so hopefully you had some time to figure out which compounds dissociate or not. And it turns out for this particular reaction, all the compounds will be soluble in water. So when we write the total ionic equation, we need to include the amount or the number of each ion, its charge, and the state of matter that it's in. So in this case, since they all dissociate in water, they're all going to have aqueous as their subscript or as their state of matter. And then from there, you include the charges, and you make sure to multiply the coefficients to make sure that you have the correct number of ions on each side. Alrighty, so after we write the total ionic equation, we need to write the net ionic equation. And for this, you're just going to find spectator ions and do not include them in your net ionic equation, because those spectator ions are ions that didn't do anything in the reaction. They were the same at the beginning of the reaction, and then after the reaction occurred, they didn't change. And when we write the net ionic equation, we're focusing on what changed we're interested in what changes in the chemical reaction. So in this case, there were no spectator ions because this side of the equation matched exactly on this side of the equation. So for this scenario, our net ionic equation will be the same thing as your total ionic equation. But a little bonus question is, did a reaction occur, and why or why not? So please open the chat and discuss, or please answer the question and explain why. Okay, so it looks like no one is replying in the chat, but that's okay. Basically, a reaction does not occur because the total ionic equation is the exact same thing as the net ionic equation. And this means that there was basically no change, like nothing changed, basically. Everything dissociated, and then it just stayed dissociated in the product's form.
All right.
So next we'll have Michael with stoichiometry.
All right. So first things first, can everybody hear me? Right, just give me like a nod or just say type in yes in the chat, please. Or do I need to speak up louder?
I think you're good.
Okay. Okay, cool. Just making sure. All right. So we'll be going over stoichiometry. So what is stoichiometry? Well, stoichiometry stoichiometry is the relationship between quantities that take part in a chemical reaction to form new products based on the amounts that they were initially given. So as of right now, I would like everyone to review their notes about how to take on a stoichiometry problem such as this. So if I were to give you 1 mole of NaCl and react it with 1 mole of lead-4 nitrate, how many moles of sodium nitrate do you make? This is the chemical reaction below, and I'll give you all a moment to think it out and see if you can see which one of what's the max amount of moles of sodium nitrate being made. Now, be sure to make sure that the reaction is balanced before you do so. And I'll do it with y'all. I can put the next slide, please. It's a blank sheet.
Great.
All right, thank you. All right. So we were given NaCl plus lead 4 nitrate. That's awkward. It's fine. To make NaNO3 plus PbCl4. All right, so now we have to make sure that the chemical reaction is balanced. So we can see on the left side, we have 1 Na, and so we do have on the right, so that's balanced. But we see that on the left side, we have 1 chlorine, but on the right, we have 4 chlorines. So we need to add in a 4, hang on, I'll just change the color. Add a 4, brown. Add a 4 right here, so we can balance out the chlorine. Wait, sorry, balance out the, right here. 4 there for the chlorines. My mistakes. So we now balance out the chlorines. Now let's take a look at the lead. So we know that the lead on the left hand, we have 1, and we also have 1 on the right. So that's balanced. But we have 4 nitrates over here, but only 1 here. So now we have to add in a 4. I can find it next to this nitrate so that we can balance it out. And since adding a 4 to our product side, we now have 4 sodium. But let's check on the reactants. We now have 4 sodium. So now the entire reaction is balanced. So it kind of works its way out if you think about it. So now then, we were initially given 1 mole of each of these, of each of the reactants. So why don't we write that out? So we have 1 mole of NaCl. We also have 1 mole of PbNO3. Oh, it's kind of messy. Oh, didn't erase. It's kind of messy. Apologies. PbNO3, 4. Right. So with stoichiometry, we have to, it's a lot of just converting from one unit to another. But it also has, so we want sodium nitrate, but we're given these 2 different mole amounts. So with our balanced chemical reaction, we can turn all of these into conversion factors to get us to that sodium nitrate that we want. So we know we have 1 mole of NaCl and 1 mole of Pb of lead-4 nitrate. So now, why don't we do conversion? So we know that for every 4 moles of NaCl, we make 4 moles of sodium nitrate based on a chemical reaction. With that, we end up getting, hold on, let me put a different color. We end up getting 1 mole of NaCl. Oh, NaNO3. Now then, now we have converted that. Now we had to look at the, we had to also convert lead 4 nitrates to units of mole of NaNO3. So we know we have, for every 1 mole of lead 4 nitrate, we make 4 moles of NaNO3. Let me make this a little clearer, just in case. Oops. And you should get about, that's an awkward color. I want that one, this one. You should get 4 moles of NaNO3. Now see that even though we're given the same amount of moles for each of our reactants, we end up with different amounts of products. So if we end up with that, that means we have this situation called a limiting reagent. So next slide, please. Okay. So what a limiting reagent is that, I'm going to erase all of this. I can erase it. It's not going away. Well, it's awkward. Wait, what? Oh, it erased. So what a limiting reagent is that you're limited to the amount that you are given, and that depicts the amount of products that you can make. So we saw that, so an example of that could be like, there's 50 students in the class, but the professor only has 48 midterms, which sometimes happens, but moving on. So how does that apply to stoichiometry? Well, in stoichiometry, you're given the ratios used to convert from one unit to another, but that also depends on how much you're given. So in the previous example, we saw that you have 1 mole. So for every 1 mole of NaCl we were given, we can only make 1 mole of NaNO3. And vice versa, if we only have 1 mole of lead 4 nitrate, we can only make 4 moles of NaNO3. But since the two of them have to react with each other at the same time, we can only make a max product of 1 mole of NaNO3. If that makes sense with everyone. So for now, I want everyone to try out this conversion. So I want to get 13 grams of C to become, I want 13 grams of my carbon to make carbon dioxide, but I only have 10 grams of carbon. So you can see that I'm limited to what I'm given in order to convert my carbons into CO2, if that makes sense. So for now, I want you all to try this out. So try converting the 10 grams of carbon into CO2, and also convert the 13 grams of carbon to CO2. So convert both grams into CO2. Convert both amounts of carbons into CO2 and see the difference in how much an limiting reagent can be, if that makes sense. We give all a little bit of time to do that. Actually, yeah. If you still have questions, let us know. If anything seems kind of confusing, let us know in the chat. So I'll be moving back into the room so that we don't disturb everybody else in the library. And I'll mute my Whoops. Technical difficulties, kids. No worries.
So basically, like, use your laptop, but mute.
Are you muted?
Okay.
Pretty sure I did. Yeah, I'm muted.
Wait.
Alright, so using my note.
Yours.
Okay. So, well, here we go. Alright, so if we can revert this, we would have 10 grams of carbon. And I know that for every
Wait, you might need to speak louder because you're using my
12
mic.
grams of carbon is equal to 1 mole of carbon. And then for every 1 mole of carbon, we make 1 mole of CO2. And then, actually, that's fine. And then for every 1 mole of CO2, you already took care of it. We made, I can't count, 44 grams of CO2. So after doing all of this, we get about 36.7 grams of CO2. For the sake of these exercises, we won't. I'm going to be picking with 6 figures. So we'll actually end up. That's fine. But now, if we were to convert 13 grams of carbon using the same process, let's see, mole C, then 1 mole C makes 1 mole of CO2, and then for every 1 mole of CO2, it's 44 grams. Oops. And that one should get you. I can demo, please. Oops. 47.6. 47.7. So with 10 grams, we get 36.7 grams. Yeah, race. Of CO2. But with 13 grams, you make 47 grams of CO2. So we can see that we're very limited to what you were given, which again goes back to the whole conversion of the individual reagents in stoichiometry. But overall, I have another example that might be a little bit more clear for all of you. So who here likes eating s'mores? Because I like eating s'mores. So here's a small example that I want you to do on your own, since for the nick of time. So in order to make it smaller, we need 1 chocolate bar, 4 marshmallows, 2 graham crackers, but how many moles can you actually make if you're given 10 chocolate bars, 50 marshmallows, and 20 graham crackers? So this paper right here would be just here for extra practices, but we have to move on for the sake of time. But if you have any questions, just post it in the chat, please. That's just a practice slide for it. That's fine.
Alrighty. So wait, do you hear an echo?
I do, but you don't hear
Wait,
it.
unplug your.
Do you have anything?
Wait, because you're muted.
I know, but yours can hear my sound.
Oh shoot. Okay, wait. Plug your earphones back in.
Sorry.
Okay, sorry, technical difficulties. Okay, so next we're going to talk about molarity. Basically, molarity is a measure of concentration. The symbol for molarity is M, and the units for molarity is M equals moles per liter. We also learned another formula in class, which is the M1V1 equals M2V2 formula. And this formula is used to calculate changes in molarity or volume for a solution. So we have a practice problem for you all to try. Calculate how many moles of hydrobromic acid are in 34.3 milliliters of 1.20 molar hydrobromic acid. So go ahead and try it out. Again, if you have any questions, please type it in the chat. Oh, yes. Oh no, okay. Yeah, so if you would like to, I recommend you take a picture of the slide because it has some really important units and formulas on it. So now let's go back to this problem. Everyone go ahead and try it out. Again, if you have any questions, please type them in the chat and we will address it. Okay, so the first step to solving this problem is to recall the formula that you need to use and know the units for molarity. So in this case, since we are given a volume and a molarity, we need to use the molarity formula to solve for the amount of moles. However, there is a problem. We are given the units in milliliters and molarity, but the formula for molarity is only in moles per liter. So we cannot use these numbers as is in the formula. We're going to have to convert to the correct units, and then from there you just fill in what you know and then solve for your unknown variable. So go ahead and try it out. And the answer you should get is 0.0412 moles of HBr. And as always, check your sig figs. Okay. So let's try another practice problem. You have 45.04 ml of 0.93 molar oxalic acid in a beaker. Then you add 3.03 liters of water to the beaker. What is the molarity of your new solution? So again, think about those two formulas that we've learned and be able to recognize which formula is appropriate for the problem. So I'll give you guys like 1 minute maybe to try it out by yourself. And again, if you have any questions, please type them in the chat. Alrighty, so let's go ahead and try to figure out this problem. So the first step you should have done is remember or recall the equation that you need to use. In this case, we're not going to use the molarity formula because we are already given, or we're trying to calculate a new molarity of a new solution. So therefore, we need to use the M1V1 equals M2V2 equation. M1V1 is basically going to be your original solution, and M2V2 is going to be your new solution. So once we know which formula to use, we're going to need to identify the variables and then solve for the unknown. So in this case, my V1 is going to be what I was originally given, which was 45.04 ml of 0.93 molar oxalic acid. The only tricky part for this problem is that you cannot use the formula if your units do not match up. So in this case, my V1 can be either 45.04 ml, or I can convert it to liters to match the liters of water that I added to the beaker. My molarity is pretty straightforward. It's already given to you. You don't need to convert or calculate anything. But we do need to make sure that whatever units we use of volume or molarity, we have to make sure that when we plug it into our equation, they must be consistent. So for my example, or when I did this problem, I used milliliters and milliliters for both sides of volume. You can use liters if you want, but I think it's easier to convert to milliliters. And then the second tricky thing about this problem is figuring out what V2 is. In this case, V2 will not be 3.03 liters of water because our new volume is the total volume of whatever we added to this giant beaker. In this case, we originally had 45.04 ml of water sitting in that beaker, but when we add 3.03 liters extra, we have to account for that original amount that was already sitting in that beaker. So to calculate V2, I'm going to do 45.04 ml plus 3030 ml of water added extra. Or if you did it in liters, it'll look like this. And then finally, your M2, that's pretty also straightforward. That's the molarity of the new solution that we want to calculate. Identifying the variables is the hardest part, I think, for these problems, but once you know your variables correctly, the math that follows after is really easy. So if you worked out the calculations, hopefully you should have gotten 0.014 molars of oxalic acid. And as always, check your sig figs. Okay, so the last problem for molarity is kind of like a challenge problem. And for the sake of time, I'm going to go through this one pretty quickly. It's pretty advanced, so when you have time, I definitely recommend you rewatch this video and try it out. But for the sake of time, I'm going to speed through it a little bit. So you want to make 0.90 liters of a 0.803 molar solution of sodium hydroxide in lab, but all you have in lab is an unlimited supply of 5.31 molars sodium hydroxide and water. So how do you make the solution? So the first step is to understand your situation and draw a picture if you need to. So here's what I drew. Basically, what we're trying to do is dilute a more concentrated solution with high molarity. In this case, in lab, we only have 5.31 molars of NaOH. What we want is a lower concentration solution. We want 0.803 molars of sodium hydroxide. So I drew a little picture here, what we have versus what you want, which is a solution that has a lower concentration. So being able to understand the situation means that you'll know which formula to use. So for this problem, you're going to use the M1V1 equals M2V2 formula. Then you're going to have to identify your variables. So here we have originally 5.31 molars, but we're not sure how much of it to use. But we do know that we want a final solution with 0.90 liters and 0.803 molars. So when we solve for V1, it turns out that we need to use 0.14 liters of the very concentrated NaOH solution. But however, we're not done yet because we don't know how much water we need. If we only add 0.14 liters of this solution into a beaker, we're not going to have the desired volume that we want and the desired molarity. So to calculate how much water we need, you're going to take the total volume, subtract it from what we already added to calculate how much water we need to add. So in this case, to make the solution, we're going to add 0.76 liters of water and 0.14 liters of the very concentrated NaOH to make our solution.
All right. So, speaking of acid and bases, we're going to talk about some electrolytes. So, what are electrolytes? So, answer the following two questions in your notes. What is a strong electrolyte and what is a weak electrolyte? And also answer this question about what would happen if you have a very concentrated solution with electrolytes. So your solution itself has a large abundance of electrolytes. What kind of properties or what kind of observations would that have? And if you kind of think about electrolytes, think of like Gatorade, where everyone says like, oh yeah, just drink Gatorade because a lot of electrolytes. So pretty much with electrolyte, I'll give you a little bit to like write it down your own. Here goes of what you think of these two questions. I can't hear you clearly, like you sound kind of. All right, so I'll try this. We're gonna skip over. All right, so this is oh, whoops. My apologies. Let's go back. All right, is this better for everyone? Hello? Much better. Okay, cool. So please answer the following questions, and we're just gonna stick with this screen, I guess. We're just gonna keep on going back and forth with it, if that's all right with y'all. All right, so why don't we move on to the next slide? So electrolytes are kind of are mainly the acid and bases. Acid and base, if you all remember from lecture. So we know that in lecture that if it's a strong electrolyte, it's a strong acid, right? And if we know that if it's a weak electrolyte, it's a weak acid. So now how to identify like if it's a strong acid or a weak acid? It mainly depends. It's how do I say it? It goes back to knowing what are your strong acids and what are your strong bases. So right in front of you are just ways of how to name a strong acid and naming a strong naming any acid and naming any base. So when you name an acid that's dissolved in water, because you have to keep that in mind, that acids are dissolved in water, so they're aqueous solutions. So naming them depends on the last syllable of the anion and the acid. So these two were taken from Dr. Kelly's PowerPoint. So these are just the naming processes, how to find it. So an example of naming an acid. So there's three different endings to an anion: IDE, ATE, and ITE. And each of them have their own specific way of how to name an acid. Like if it ends in IDE, it's hydro blank ic acid. ATE is blank ic acid, and ITE is blank ose acid. So I have the three of the following, where each of the anions have the three different endings. So nitrate, which is NO3 minus, becomes nitric acid because it has an ATE ending. You just drop it and just stick it where the blank part is.
Nitrites, which is NO2 minus, becomes nitrous acid. Again, applying the same rule. Just take out ITE and then put the rest on the blank space. And then we have fluoride, which is F minus, not fluorine, where you just take out the IDE and just put the rest in the blank space again. So it becomes hydrofluoric acid, if that makes sense with everyone. Bases are kind of more simple, I would have to say, to name. So when you're going to dissolve a base in water, it just becomes the name of the cation that it has plus hydroxide. So example, NaOH. You know that Na is the cation, and then OH is the symbol for hydroxide. Sorry, OH minus is the symbol for hydroxide, so it becomes sodium hydroxide. Barium, which is a +2 charge, requires 2 hydroxides instead of 1, but it still ends up becoming barium hydroxide, not barium dihydroxide or barium duo hydroxide. It's still the same. So it's just always the cation plus hydroxide when you name them, when you name bases in water. If the bases are not in water, then they are considered salts, since they have not dissolved to become aqueous solutions, if that makes sense. Also do note that when you name an acid and it's not in water, like example, if I can find my mouse, like, let me see this, like H. Oh, well, we can like, okay, well, okay, I can't really see. That's right, I'll just put on this one. H2S. So if you know that in H2S that there's no like aqueous symbol right here. So if I put an AQ right here, it's an acid. However, if I write down H2S like this, like H2S without this AQ right here, then it'll be called, I'm sorry, it'll be called, can I erase? There you go. Hydrogen sulfide. So in the midterm or any of the like the quizzes, make sure that you see that AQ next to your acid or base. Make sure that you see the AQ in your acid, because if without that AQ, then there's a different naming for different naming for them. So why don't we move on to the next slide? Oh, sorry, it's not the erase button. Why don't we move on to the next slide? And that would be, why isn't it going? Wait, next slide. Next slide. Oh, I gotta click it. Oh, my bad. All right, why don't we move on to redox? So we had a lot of requests for redox reactions, because that's what you'll be doing for your lab experiment this upcoming week. So when you do a redox reaction, it is, oh, there's no, okay, awkward. When you do a redox reaction, so what is a redox? So a redox is the process of oxidizing or reducing compounds by gaining or losing electrons. In the discussion that Dr. Kelly posts, there's a more descriptive idea of how redox is constructed. So I suggest that all of you were to look at that like after the session, and also just prepared for going over redox Monday. Prepared to go over redox on Monday. All right. So in redox, it's just a combination of two reactions. So there's an oxidation reaction and a reduction reaction. So if you just take out if you just take the beginning of them, it becomes redox. If you think about it. So an oxidation reaction, you are losing electrons. What I mean, so right now it may seem kind of like unfamiliar language, but on Monday you'll see like what I mean by losing electrons in an oxidation reaction, and also the requirement of using a reducing agent. And then for a reduction reaction, it's just the opposite. where you're gaining electrons, but it requires an oxidizing agent. So how I remember them was oil rig. So how it works is oil. So it's oil rig. So it's OIL, which is oxidation is loss, and rig is RIG, which is reduction is gain. If that makes sense with everyone. All right. So that's one of the ways of how to memorize oxidation reactions. Another one is using Leo the lion goes grr, where it's loss electrons is oxidation and gain electrons is reduction. So these are like the different types of acronyms that like will help you understand what I mean by that. And do note that when you using an oxidation reaction, you need a reducing agent, and for a reduction reaction, you always need an oxidizing agent. So that's not so it's always hand in hand thing. So it's not always, so you're not using the same for each of them. So you don't use an oxidizing agent for an oxidation reaction, and this is the same thing for a reduction reaction. It's always the opposite of it. So if it's an oxidation reaction, reducing agent, reduction reaction, oxidizing agent. All right. So why don't we move on to how to balance a redox reaction. So right here is just the steps of how to solve a redox reaction. I know that it may seem kind of long and scary, but no worries. Just no worries. When you go into a lecture on Monday, you'll see what these steps look like firsthand. But if y'all have any other questions about it, just please post them up in the chat. So when you solve a redox reaction, like this one right here. So you have MnO4 minus plus H2O2 and Mn2 plus O2. So what we want to do is we want to split it into half reactions. What I mean by that is, this is where we're gonna do some stratting, people. All right, we're gonna see some weird inception stuff right here, kids. All right, so splitting half reactions is as follows. So when you split half reactions, you're trying to match whatever element on the left is with whatever's on the right. So I want to match MnO4 with this one. So I'm going to make its own little half reaction right here. So MnO4 minus makes Mn2 plus. As of right now, it seems kind of like, it seems very confusing, like what are you doing? But after lecture of going over redox reactions, come back to this video and then it will be maybe a little bit more clear. So I'm splitting these two into half reactions. So I'm reacting, and then, so hold on, let me just finish my half reactions. So I'm permanganate, which is this ion right here, and hydroxide forms Mn2 plus, which is manganese 2 plus O2. So none like using like innies and indies and outies and outies, that method won't work with redox reactions. So they come up with half reactions method. So instead of solving one giant reaction, you're taking it piece by piece, if that makes sense. So I know that in my left-hand side, I have a manganese right here, and I have a manganese right here. So I just equate them to each other. So I have permanganate, which is on my reactant side, and I'm gonna make it to become manganese. And for my peroxide, which is H2O2 over here, I'm gonna react it together to make O2. So that's step one, creating them into half reactions. Now, this is going to get some wonky stuff. So step two was to balance all hydrogens, oxygens, or electrons. So as of right now, the only element that I have that's neither of those three that I stated is manganese. And I can see that on the left-hand side of my first half reaction, I have one manganese, and on the right, I only have one. So that balances out. And on the bottom, I don't have anything besides hydrogen or oxygen. So I can't do anything with that as of right now. So then, the third step to solving redox reactions is to add oxygen. To add oxygen, you have to balance out the oxygens by adding water. So since we can't get really oxygen by itself because it's the cost efficiency of it, but it seems kind of babbling by that point. But so in order to balance out oxygens, we have to add water in order to balance it out. So why don't I just get that going? So we look on the left, we can see that, what happened? Okay, so we can look on the left, we see of our first half reaction, we see that we have 4 oxygens, but on the right, we only have 0. So what we do is we add, this is a terrible color, what am I doing? So what we do is we add the same amount of water molecules. So in this case, I'm adding 4 water molecules to balance out the oxygens, if y'all can see that. So I note that for every 1 water molecule, I have 1 oxygen. So since I have 4 oxygens in my reactant, I need 4 oxygens over here to balance it out. Now then, why don't we move on to the bottom part? Now we see that peroxide has 2 oxygens, and on our right-hand side, we have 2 oxygens. So it's balanced. Conservation of mass, if y'all remember that theory. So now that our oxygens are balanced, now why don't we move on to balancing hydrogens. So how we balance hydrogens, we have to add acid to it. So adding H pluses. So if I can find a good color. All right, this is a wonky color. So let's look on our first half reaction. We see that we have manganese over here, and we see that we have 4 water molecules. But there is 8 hydrogens. So 4 times 2 equals 8. But over here on our reactant side, we have 0. So what we do is we have to add the same amount. Well, we don't add the same amount. We have to balance out the hydrogens by adding acid. So right here, we have 8 hydrogens being added to our little half reaction, because we're adding it as acid. As acid, you can get it as you can get it from like your strong acids mainly. That's what you were to get. Just finish it right here. All right. Now then, on the bottom part, we have peroxide and O2. So we know that peroxide has 2 hydrogens and oxygen, and on the product side, we only have 0. So what we have to do is we have to add in 2 more hydrogens to balance it out. If that makes sense with everyone. I know it seems kind of confusing at first, but you'll see what I mean, and you'll see what I mean when Dr. Kelly goes over this more in depth, because we're just speedrunning this. So after balancing that out, so now we have balanced out our hydrogens on the first half reaction and on the bottom. Now then, after balancing out the hydrogens, now we have to balance out charges by adding electrons. So how that works is we have to add electrons to the more positive side. So if we think about this, we have 8 hydrogens over here, which all have a +1 charge, and we only have 1 manganese over here with a negative charge. So it's +8 minus 1 is equal to 7, +7. So this is +8 minus 1. It looks like a 7. I think about it is equal to 7. Positive 7. 7 plus. So this over here on the reactant side is a 7 plus charge. On the right side, we have a 2 plus charge, because we know that the charge of water is 0. But we know that manganese is a 2 plus because it has a charge over here. So since we have a 7 plus over here and a 2 plus over here, we need to add electrons on the more positive side. So in order for me to get from 7 plus to 2 plus, I need to add 5 electrons to my reactant side to balance out the charges. Again, this seems confusing, but we're speed running. So now we have an overall balance charge of +2 on the left and +2 on the right. Now then, On the bottom part, we have an overall charge of 0 on our reactant side, and we have a 2 plus on our product side. So now we have to add in 2 electrons on this side, so we can balance out the overall charge of the redox reaction. So now it's 0 is 0, if that makes sense. Whatever one. So now then, now that we have all of that, now we have to do is balance out charges. What I mean by that is that we have to make sure that all of our electrons are to cancel out. So on the top part, we have 5 electrons. And on the bottom reaction, we only have 2 electrons. So what we have to do is we have to make sure that we multiply the entire reaction to balance out the electrons. So I know for a fact that 5 and 2 are not divisibly possible with each other. So I have to multiply the top reaction by 2 to get 10 electrons to get 10 electrons on the left, and then by multiplying 5 on the bottom, I get 10 electrons on the right. If that makes sense. All right, so now what I'm going to do is after balancing out the electrons, now all we have to do is just add all of these together, and then you simplify it. So by adding all of these together, we will end up getting oh, dang, I gotta write it out, don't I? All right, 10 electrons plus 16H plus. Your internet is unstable. Well, you're unstable internet. You ever thought about that? Plus 2 MnO4 minus. Make sure that you include everything on the left. So plus 5HH 2O2 produces 2Mn2 plus 8H2O plus, I can't count, 5O2 plus 2NH plus 10 electrons. Yeah, you're right. I'm just gonna freaking get the, there we go. Go away. All right, we're gonna put this back in. 10H plus. All right. Now then, for the final step, you have to simplify the entire reaction. So what we see on the left, we can, what we see on the left and what we see on the right, they cancel out. And we can simplify even more by just, how do I say this? By taking any like terms and then combining them and bringing them to the other side. If y'all remember your algebra days. I don't. So I guess for since we got 1 minute left, I guess the simplified version for this entire reaction will be, I'll put it up here. So it'll be 8H plus. Oh, sorry, not 8, 6. I can't count. Oh, the awkwardness of not able to count. It'll be 6H plus 2MnO4 minus plus 5H2O2 produces 2Mn2 plus I need water, 8H2O plus 5O2. And that's it. So seems kind of messy, but hopefully I'll work on like presenting that next time, and we'll work on it better. But moving on. So that pretty much concludes our session. We're right on the dot with 1 o'clock. If you have any other questions, just come in and lecture, and we will be in the front just camping. Yeah. So.
And then if you came late, please remember to sign in on the Google Docs sign-in sheet. If you have any other questions, like last-minute questions, we'll like stick around for a little bit. And yeah, that would be it. Thank you so much for coming, and we'll see you guys in lecture. Bye.
Bye. How do I record? How do I end recording?
Yeah, do.
All right.
Well, actually, let's wait.
That's so weird.
I know. Wait, let's wait.
Hold
Wait,
on.
dude, you don't have to like erase everything. You just put here, and then it'll. Yeah. Oh, actually, yeah, stop recording.
Where's the recording? Oh, wait. Stop share. No, it's not that. Board control. Abort mission. Chat room. We have